Hello everyone, my name is Marshall Edens, and this is my final project report for GEOG481. Here's a brief overview of my project idea. In short, I wanted to create LiDAR-based maps to be used by high school students in an experience that we call the Outdoor School near Lancaster, Pennsylvania. I originally thought I would use a combination of LP360 and ArcGIS Pro for this project, but I ended up only using LP360. I used 6 LAS files downloaded from the PASDA clearinghouse, which fully encompassed my area of interest. Here is relevant information regarding the data, including the coordinate system and point spacing. The remainder of the presentation focuses more on how the project went and what I learned. Part 1 was the data upload and visual inspection. Once the 6 LAS files were uploaded into LP360, I visually inspected the data. I opened the Live View window to observe the classification scheme and looked at the number of points in each class. I decided not to alter the classification scheme because the metadata indicates that the data was recommended for creating hydroflattened DEMs of 2.5 foot cell size, and I knew this would be sufficient for my purposes. Vegetation was separated into 3 classes, but most of it was in medium and high classes. A visual inspection of the profile view shows this peculiarity where low vegetation is shown in pink, medium vegetation is in blue, and high vegetation is shown in green. The pink points are very few and are within or just barely above the ground points in orange. The yellow arrow here points to one of them. The next step was to create the boundary as a shapefile in LP360. I first went to the Nature Conservancy website to see if any readily available data was offered, but I could find nothing. A trail map produced by the Conservancy was available as a PDF file, and I was able to trace the shape onto a piece of white paper over my computer screen using a pencil. I made sure to include some of the adjacent roadways in my tracing to use for alignment. I then zoomed to a scale of approximately 1 to 12,000 in LP360, which aligned very well with wooded area and my traced roadways. I think this method worked surprisingly well. My boundary was strikingly similar to the Conservancy map. If more accuracy was required, perhaps I could use a GPS device to pin certain locations, like landmarks and corners of the park area, and force my shapefile lines through those points. But for my purposes here, this low-tech method worked great. Here are some photos of this low-tech process of tracing over the Conservancy map, then applying the tracing over LP360 base map to create the boundary shapefiles shown in lime green on the right. The outlines of the trails, streams, and plotting of outdoor school points of interest are here as well, but will be discussed in the next few slides. The next items to add to my map were the trails and streams that students would be interacting with in the field. I knew that I wanted to create sections of trails for measurement purposes later. For example, I created one line feature from where our bus drops us off to the home base located in the preserve. In this way, the measurement for that leg of our journey is built into the map, yet visually the trail segments are joined for visual continuity. I used the same tracing process as described in the previous slide, but realized quickly that more accurate placement was necessary. For example, my original stream lines were often clearly outside of the stream banks, and my trail lines crossed the streams at points which I knew were incorrect based on my experience with the terrain. This inaccuracy was easily seen using a ground tin filter up close and by forcing 100% resolution. I used the shapefile editing tools, mainly the Select, Edit, and Add Vertex tools, to adjust the placement and join my separate sections to create visually continuous trails and streams. The image here shows a screenshot of me bringing vertices within the stream bed along a stretch of Steinman Run. This was a very satisfying operation. The last feature I wanted to add were the stations that students visit throughout the day. I created a final shapefile of points at these locations based on my knowledge of the terrain and landmarks. Part 3 of my project workflow was to drape trails, streams, and station points on top of the elevation model. To do this, I modified PCTs created during the course. Specifically, I used the centerline pure drape PCT for trails and streams and conflation PCT for the stations. Because the trails climb drastically in elevation in some parts of the preserve, I adjusted the respacing values from 25 feet, which we used in our hydroflattening lab, to 10 feet. This gave my trails elevations sampled at better resolution and could be used to calculate valuable statistics, such as exactly how much elevation change occurs from base camp to where our bus picks us up. Here are some of the results of the draping process. The table on the right is the feature analyst window for the 10 station points, now with Z elevations in the far right column. The 3D viewer window on the left shows trails in yellow and streams in blue hugging the terrain. I stretched the vertical axis multiplied by 3 to better show the high and low sections of the preserve. This is a tool I would use when producing views to show students and to discuss with them the terrain before they arrive for their outdoor school experience. I originally listed symbology adjustment as a separate step in my workflow, but I found myself making these adjustments all the time to suit my purposes. I settled on the colors shown here. An interesting effect I noticed but was unsuccessful in fixing is the buried look that my station points took on after draping them to the elevation model. I can see why this happened and can relate this to video games I used to play as a kid, when I would see player avatars break through what should be solid surface models. I think ArcGIS Pro would allow me to adjust the labels and symbols better than LP360. I did look for a way to adjust this in LP360, thinking I could use the PCT settings to add a few feet to the elevation during the draping process. This would move the points up out of the way of the intruding hillsides. In order to complete the look of a topographic map that I was going for, I needed to create slope and hillshade rasters. I first did a manual assessment of the ground points to determine what cell size I should use. The LAS file metadata already assured me that 2.5 foot cell size would be appropriate, but I wanted to verify this. I zoomed in until I could see individual points spaced apart. I drew a simple 10 foot by 10 foot box and counted the points within. 30 points on average in these boxes produced a ground point density, an average ground point density of 3.2 points per square meter. This told me it was safe to use 2.5 foot cell size for my rasters, but I erred on the side of caution and used 3 feet, just to be safe. This resolution was plenty to produce rasters that look appropriate at scales I would be using to display to students. Here you can see the resulting slope and hillshade rasters. The last thing I wanted to do in my project was to estimate tree height near the tree ID station. We have our students use simple trigonometry to estimate this in the field, and I thought that I might be able to find a specific tree that we like to use, but the canopy on the base map image is too dense and the profile and 3D views didn't improve my ability to locate that specific tree. But I was able to use the profile viewer to isolate a section near to where our target tree is and found that trees in that area are about 90 feet tall. My calculations can be seen at the bottom half. I'm quite happy with the result of this project. My goal was to produce maps that could replace the hand-drawn ones we have used for the last 20 years. Here is a map showing where we would spend most of the day. I would use this map to discuss the itinerary with students, show them where they would be dropped off by the bus, to show them where we would be staying in the loop trail where our stations are dotted, to show them where not to stray, and to show them that they would cover more than 100 feet of elevation change on the trail. Finally, I would like to share that I still have unfinished business with this project. I still would like to use GIS to create more robust virtual experiences for our students who can't come with us to the outdoor school. I still think Esri's story maps would be great for this, and I look forward to figuring that out later. Lastly, I was also excited to now have more questions to answer. I saw these pockmarks in the terrain, a curious phenomenon that my students will likely wonder as well when they see these maps. I will be taking students to outdoor school at the end of May, and I can't wait to see if they can solve this mystery.